Hi everyone, welcome to Nטפim's Growing Organic in Soilless Media webinar. My name is Eli Merkel, I'm the Global Training Manager of Nטפים, and it's really great to have you all here. We have many people from around the world, so good morning, good afternoon, good evening, even I think good night for some of you. So this webinar is actually continuing our last webinar from several weeks ago about soilless irrigation. In this webinar, in the upcoming 90 minutes, we'll have the pleasure to host one of the world's experts in, we show you, yes, okay, one of the world's top experts in growing organic in soilless media, Mr. Boaz Guy, Nטפים Chief Agronomist in Mexico. As probably some of you already noticed, you can contact us using a Q&A panel, okay? It's supposed to be on your right. Okay, you can write us questions during the webinar. Please feel free to ask questions and comment. We will be monitoring these questions all along the webinar. Okay, we'll do our best to answer, and some of the questions we'll try to answer immediately. Some of them will wait for Boaz to refer later. Please notice this webinar is recorded, okay, and it will be available in several days in our website, nטפים.com, in the Precision Irrigation Academy. We will try also to share with you the link later. So meanwhile, I think I covered everything. Before starting, and in order to give a chance to some additional people to join, please, I would really appreciate if you could participate in a poll. Let's start the poll, okay, and answer this quick question, okay, this quick question, which crop do you grow organically? So I see some of you already started to answer, so we'll really appreciate your answers. Okay, let's see. So as you can see, the option, you're supposed to see the poll on your screen now. The options are tomatoes, okay, bell peppers, cannabis, berries, or something other. So we're getting this, getting the answers right now. Great, thank you guys, thank you for sharing. Let's give it a few more seconds. Wow, it's really interesting. Okay, few more seconds to answer, and I'm closing the poll. Okay, so it seems that we got all kind of answers. Okay, let's see. Okay, so many of you growing tomatoes. Okay, other. Okay, berries, bell peppers. Okay, really interesting. Okay, guys, I think we're quite ready. So Boaz is already online and with us. So with no further delay, Boaz, the stage is yours. Thank you.
Okay, thank you very much, Eli, for the introduction. Hello, everyone. Welcome. I hope that you're all healthy and safe. The presentation that I would like to share with you today is about growing organic in soilless media. We'll talk about, let's go to the agenda. We'll talk about why growing in soilless, what are the challenges in organic nutrition, fertilizer quality, pH control, and special applications of beneficial products. Then we will go through Nטפim's solution for organic products and maintenance recommendations. We'll also have time to answer some questions, as Eli said, during the presentation and also at the end. Okay, so let's start. Well, organic agriculture, especially growing in soilless, is rewarding, but it is also very challenging, as you can see in the image. There's no doubt about it. Being close to the farmers, seeing their challenges in the daily operation, looking together with them for solution, led us Nטפים to develop an organic concept that includes special products, special design, and a knowledge in what to do and also in what not to do in order to ensure long duration of the equipment and high irrigation performance. This is the objective. What are the challenges? What are the technical solutions that we offer to our clients here in Mexico and in other places also? This is what I will try to present and describe in the presentation. I hope you will find the presentation, the information interesting and useful, and we'll start. Well, organic agriculture keeps on growing. According to Allied Market Research 2016, global organic food and beverage market has been growing at an average annual rate of 16.4% since 2014. Organic crops can be very beneficial, cashing 2 times and sometimes more than conventional crops. So the market is there. It keeps on growing where people want to eat healthier food. And there's no doubt that in the future we will see more and more organic farmers. But is soilless cultivation organic or not? It depends where. In the US, there is a debate. Some say that it is, some say that it's not. But the actual situation is that you can grow organically in substrate in the US or in countries that provide product to the US. So Mexico is one of the countries. We grow here in substrate, soilless, organically. In the European Union, as you can see below, underlined with the blue line, there is a very clear regulation, and they say that it's a clear issue. Growing in soil is one of the core characteristics of organic production, and they don't allow growing organically in soils. Why to complicate? Organic agriculture has its complexity. Why to complicate further more? And grow of fruits isolated from the soil by a container. And in this small volume, we control all conditions to bring them to the optimum. pH, it's very important to control pH to optimize nutrient absorption by the plant. Salinity, remember that we apply salts by the water, by the irrigation water, and by the fertilizers that we apply. In our irrigation management, we have to ensure a continuous washing of excess of salts. If we have too much salts or salinity, we can have toxicity problems. We can limit the water absorption by the plant. Oxygen, obviously, it's very important. Roots has to breathe. They need water, but they need also oxygen. We always try to maintain the right balance between water and oxygen. We do it with choosing the right texture of the substrate and also by the water management, by the irrigation management. Phytosanitary, obviously, when we keep the right condition in the root zone, we reduce dramatically the incidence of diseases. But if we have a disease, we can apply a fungicide or we can apply insecticide, and it goes directly to the root zone to a very small volume where its efficiency is very, very high. So controlling the conditions, giving the plant best conditions, we get higher and better yields. Another issue that gave an advantage to soilless before is shorter time to get the organic certification if we compare with soil. But is it true? Unfortunately, not anymore. A few months ago, the regulation of 3 years waiting time for soil was applied also for soilless. So we also have to wait 3 years, even though when we grow in soilless. This is applying to the US market. As you can see here in the photo, this is a typical, we can say, typical one of the most popular substrate for blueberries in Mexico. It is used for conventional growing and also for organic. You can see that it is made of 3 base principal components: perlite, the white particles that gives some water retention, but mainly aeration through the years. Remember that blueberries are long living plants, many years, 10 years, and even more. So we need to maintain the aeration of the substrate for many years. Then we have the cocoa peat or cocoa fiber, which gives water retention. Also, it is very, it keeps fresh temperature in the substrate, or cool temperature. And we have the peat moss, which gives water retention, a high cation exchange capacity, and also low pH. But not every soilless media can be used. It has to be certified. And it has to be certified by OMRI. OMRI is the Organic Materials Review Institute in the USA. It has to be certified by OMRI. Luckily, 2 of the most used substrates for blueberries in Mexico already have the organic certification. The first is a Dutch product called by the company Legro. It's a Dutch company. It is a mixture, very, very similar to the photo that we saw before. It's a mixture of peat moss, cocoa peat, and perlite, and it has a OMRI listed certificate, making the product suitable for the American organic market. The other product, the other substrate is Coco Peat by the company Pelemix. Pelemix is an Israeli company producing in Sri Lanka. It's a very good mixture designed especially for blueberry, very light and very big texture substrate. It has several layers. And it has the OMRI listed certificate and also the label, the OMRI label on its product. What are the challenges in soilless organic fertilization? We'll go through all of them. The first one is fertilizers quality. It's a big challenge. The second is the pH control. And the third one is beneficial product application. Let's start with fertilizers quality, which is the main issue. The first point is a low solubility of mineral fertilizers. Mineral fertilizers, even though they are minerals, they can be used in organic agriculture, but they have low solubility. The one that has the highest solubility is the potassium sulfate. And as we can see here, it has a solubility of 11% at 20 degrees. We all know that we can have less than 20 degrees, maybe 10 or less, and the solubility will go down to 7–8%. The other one is the source of calcium, which is very limited. We don't have many sources of calcium in organic agriculture. So many people use calcium sulfate, which has it says on the label on the sack that it is soluble, but look at the solubility that it has, 2 grams per liter, which means 0.2%. It's very, very low. There are some other sources of calcium, but they are more expensive. Oops, I went too far. Okay, so we have low solubility of fertilizer. We have a problem. How do we solve it? How do we increase injection capacity? Usually our injection unit comes with 5 ventories. The biggest one is of 1,000 liters per hour. Sometimes it's enough. We connect, as we can see here. A minute, I'm trying to draw something. Okay, we can see in the image below the table that we connect 2 ventories to the same tank to have, instead of 1,000 liter injection capacity per tank, we have now 2,000. Okay, so in the first NetaJet, we have 3 tanks connected, 2 of them with 2,000 liters per hour capacity, and we are left with a single venturi with 1,000 liters per hour, which is used for special application, microorganisms. We can use it also for system maintenance. The first 2 tanks we use for proteins. In the second NetaJet, which is the slave, we have the same arrangement with 3 tanks, 2,000 liters per hour for the first 2 tanks, and we are left with the third one with 1,000 liters per hour, which is used usually for the acid. We'll talk about the acid later on. Okay, the second issue with the fertilizer is that they have high content of total suspended solids, what we call TSS. Fertilizer contain proteins, very small particles floating in the fertilizer that pass through the 130 micron filter. But in a static situation, they gather to form bigger and heavier particles that sediment and may clog the drippers. We can see on the left side the analysis of the fertilizer provided by the company, the fertilizer company, and it has as an organic matter 38%. It means that we have organic matter which is not soluble floating in the fertilizer. That doesn't mean that this fertilizer can be used. It can be used, but with the right precaution and systems. The fertilizer provider recommends, even though it is a liquid fertilizer, it recommends to dilute the fertilizer in a ratio of 1:10. 1 product and 1 part of product, 9 parts of water. And they also recommend as maintenance, and they say, even though the product is filtered, it is recommended to wash periodically the drip lines in an intervals of 1 week. So they're aware of the problem. and they recommend to dilute and to give a frequent maintenance. So we have a problem. We have fertilizer with high TSS. What do we do in order to solve it? We put high filtration capacity on the fertilizer tanks. Usually for conventional fertilization, we put only 1-inch filter going out of the fertilizer tank. In the case of organic, we put 2-inch filter, and we put 2 of them. Okay, this is in order to increase the filtration area of the fertilizer. In some cases, as you can see on the right picture, we have an organic fertilizer based on fish emulsion, and the farmer asks us to put 6 filters of 2-inch. Okay, so it is important. It is important to have high filtration capacity in order not to stop the irrigation and clean the filter. Okay. Let's go to the picture on the left. We can see that the suction of the fertilizer is being done from a point a little bit elevated. And at the bottom of the tank, we have the washing outlet. The washing outlet has to be in the lowest part of the tank. We recommend that every time that the tank is finished and we are left with some sediments at the bottom, not to try to dissolve them again. They will not get dissolved, so it's better to wash the tank every time that it is finished. This is in order to prevent accumulation of the solids. When we make a hole in the floor of the tank, there is an issue of warranty that has to be dealt, but it can be solved. The injection point is a little bit elevated in order not to suck sediments and to suck a little bit cleaner solution. Okay. Why do we need another filter in the field, as shown in the pictures, if we already filtered the fertilizer going out of the tank, and also in the irrigation room on the main line we have another filter? So the fertilizer already passed through 2 filters. Why do we need a 3rd filter in the field? There is a problem that the fertilizer, when it flows, it doesn't sediment. It doesn't react between there's no reaction between the fertilizer or the minerals. The problem is when it is in a static situation, when, let's say at night, for example, if we have the pipe full of fertilizer solution, during several hours, small particles can gather, as I said before, can gather and can form bigger particles. So it's better to filter them again before they go through the valve to the drippers. This is why we put manual filters, also 130 microns. The diameter depends on the valve diameter. It can be 2 inches, 3 inches, so on. Some more quality issues with the fertilizer. Protein fertilizer form bubbles. The same as when we make a milkshake and we put air into the milk, we get bubbles. The same happens with protein fertilizers when we mix them by air. When we inject, when we make our calculation of how much fertilizer we want to inject, we consider a liquid fertilizer. And if we have bubbles, sorry, there is a mask. If we have bubbles, we can't calculate and we can't measure correctly because the liquid is mixed with air. So how to measure it properly? It's difficult. So we want to avoid the bubble formation in the fertilizer tank. The fourth point, quality issue with fertilizer is that non-chelated micronutrients may get oxidized. Unfortunately, we cannot use chelated micronutrients in organic fertilization. In conventional fertilization, we can use chelates. Chelate is a molecule that covers the metal or the micronutrient and prevents its oxidation. Some micronutrient products are based on humic acids, which also chelate and protect the metals, but they're expensive. Some people use it, some people don't use it. Many people use sulfate-based micronutrients, and we know that when we put iron sulfate in the water, we dissolve it, the sulfate separates from the iron, and we have the iron totally exposed and can be oxidized. So we try to avoid mixing this tank of micronutrients by air. We do it with a mechanical agitator. As you can see on the left picture, we can see the mechanical agitator for protein-based fertilizer and for micronutrients. On the right side, you can see the air blower for mineral fertilizer. There's no problem to mix a mineral tank fertilizer like calcium sulfate or potassium sulfate, magnesium sulfate with air. So we do it, we mix the solution for proteins and for minerals. The mechanical agitation, it's better to have it with a velocity control. Why do we need, here you can see in the image, several solutions for or installation solution for a mechanical agitator. It has the motor, then it has like a rod going down, and at the end it has some propellers that goes around and agitate. Why do we need the velocity control? We use high velocity when we prepare the tank or early in the morning before starting the day. At night, it's not so necessary to mix the tank. So in the morning, it's better to start with high velocity. And during daytime, we can go down to low velocity and to have a continuous agitation, but on a low velocity. Another issue, remember that we have an automatic system or injection unit. For soilless, we must have an automatic unit. So it has sensors, and sensors may get dirty by fertilizers. So on the right side, you can see the pH sensor covered with organic sediments. And on the left side, you can see the EC sensors, or the EC sensor also covered by dirt. So this sensor may give some readings, but obviously when a sensor is dirty, we will not have the right readings. So we recommend to take them out once a week at least and clean them. If we leave the sediment to accumulate and to get dry, it will be difficult to take it off, and we'll have to use more aggressive ways of cleaning, which can damage the sensor, especially the pH sensor is more delicate. So in our unit, as you can see on the left picture, there is a quick opening that allows us to take the sensor very easily and clean it. So there's no reason why not to do it in high frequency. Another issue is that organic fertilizers, or it can be also minerals like calcium sulfate, may leave sediments on pumps impellers. As we can see here in the photos, this is a very drastic situation. It is a problem. How do we solve it? First, let's see the NetaJet bypass circuit. We have the main line on the right with the filters in the middle, and we have the NetaJet on the left side. Okay, it has the pH and DC sensors. It has the ventures. There is a pump, the booster pump that make the water pass through the ventures. It goes to a mixing chamber where fertilizer and water are being mixed to get a uniform solution, and then it goes back to the main line, going through the filters, getting filtered again, and mixed to get a very, very uniform irrigation solution before it goes to the plants. So we inject the fertilizers. I'll try to draw again. I don't know why I'm not able to do it. Well, so we have now you can see we have the fertilizer injection. So in the first horizontal pipe after the ventures, we have a concentrated solution because it receives the injected fertilizers, and then it goes to the booster pump, and then to the mixing chamber and to the main line. But in this pipe, this horizontal pipe that goes to the booster pump, we have high concentration of fertilizer. So we don't want to leave this concentrated solution in the pump. So what we do, a minute. This is a screenshot of our controller, of the configuration menu, where we can give a time off for the booster pump. So we let it work several seconds more in order to bring a solution which has only water or very diluted fertilizer solution back to the booster pump. So we leave the booster pump during night or between irrigation cycles with a very low concentration solution. Okay, this is a problem that we saw, and we have a solution. Another issue with fertilizer quality is that fertilizers may be acidic. Not all of them, but some of them, especially proteins, are acidified. Acidifying the proteins give them more stability, and also it is the phosphorus source. So phosphoric acid, what we see here as the fertilizer on the left, 571, the 7% comes of phosphorus come from phosphoric acid. Comes from phosphoric acid, and this is why the fertilizer is acidic. So when we try to adjust EC by injecting more fertilizer, we also low the pH. So it makes difficult the EC adjustment to reach the EC target if we define an EC target. More issues with fertilizer quality. There may be a chemical reaction between fertilizers in the pipeline. I already mentioned this point, but let's go a little bit deeper. When growing in soilless, fertilizing is usually done with a balanced nutrient solution. We all know it. That contains all macro and micronutrients. But in organic fertilization, if we combine all the nutrients in the same solution, we can have problems. Calcium may sediment the proteins and cause clogging. Therefore, we recommend to divide the nutrient solution and apply proteins and minerals separately. In the graph, you can see this is a graph actually from our monitoring system called before you manage, now it is NetBeat. The red line represents the percentage of volumetric humidity in the substrate measured by delta T sensor. So, and the light blue columns represents the irrigation volume measured by a small water meter connected to the drip lines. So we can see that every irrigation has a response in the sensor. What I want to say here is that we start the day with proteins applications. We don't want proteins to be left in the pipelines for the night, so we apply them in the morning. And then we stop applying, okay? We apply proteins in the morning, the first 3-4 pulses. Then we make a separation in the pipeline with 1 pulse of water. Water means acidified water. And we know that we are not washing the proteins that are in the pipelines with this small pulse, but we create some kind of separation between proteins and minerals by giving this water pulse. Then we continue with several mineral pulses, applying potassium, calcium, magnesium, and we finish the day with a pulse of water to create a separation for the next day, okay, before injecting again proteins. Some more issues. Many fertilizers are based on sulfates, magnesium sulfate, potassium sulfate, calcium sulfate, micronutrients like iron, zinc, manganese sulfate, etc. That leads to sulfate accumulation. Plants don't need so much sulfates, and what plant doesn't uptake remains in the substrate and accumulates. And we have to take it in consideration and wash it periodically. Remember that every time we wash, we can't wash only the sulfates, we wash everything. Good minerals and bad minerals, it's a total wash. So we have to wash and then fertilize again. Another agronomical problem is that availability of nutrients to the plants in many cases is difficult to calculate. Okay, we calculate our nutrient solution considering the percentage of every nutrient in the fertilizer, but we don't know when it will be released from the organic complex. Okay, we don't apply it available to the plant in the available form. We apply it as an organic complex. An organic complex has to get demineralized and liberate its nitrogen, for example. And it takes time, and we don't know exactly how much time because it depends on other factors like on temperature, like on biological activity. So it takes time, and we don't know exactly when. Since EC control is difficult, as we saw before, we usually inject by quantity. Okay, it is defined cant in the controller, or in a proportional way, liters per cubic meter, or pcant as it defined in the controller, but we don't ask for an EC target. We saw it's difficult, it's not accurate to ask an EC target in organic. And since the filters of the fertilizer tank get clogged frequently, it is important to measure the fertilizer flow and not to base or to rely only on the calculation done by the controller. Okay, so we usually, as you can see on the image, we use a fertilizer meter for each tank. In the photos, you can see the NetaJet unit. Okay, it has the booster pump, it has the venturies, and every venturi has a fast opening valve to control the injection through the venturi. These valves open and close many times during a pulse of 2 minutes. Every time that the valve closes, fertilizer flow should be 0. But because of inertia, the fertilizer meter keeps on rotating, which creates an error in the measurement. Okay, many pulses, many errors. So we have to avoid it. This is why we put a vertical pipe, as you can see here in the photo. This vertical pipe stops the additional rotation of the fertilizer meter when injection pulse is over. So let's make a short recap or summary. What are the challenges and solutions? First of all, low solubility of mineral fertilizer. What is the solution? We use high injection and high volume tanks. The tank volume is very important because remember that we irrigate with short pulses and very frequent. If we have high injection rate above 10 liters per cubic meter, and we have a small tank, the tank will get finished very fast, and we'll have to stop the irrigation to prepare another tank before renewing the irrigation. And preparing an organic tank takes time. We have low solubility fertilizer, and it takes time. We'll have to stop irrigation for a long time, something which is not recommended in substrate. So we use high volume tanks in order to reduce the frequency of the tank preparation. High content of total suspended solids. We need to have efficient filtration going out of the tanks in the irrigation room on the main line and in the field near to the valves. Bubble formation in fertilizer tanks is a problem. We use mechanical agitation to solve it. Oxidation of non-chelated micronutrients, we solve it with a mechanical agitation of this tank. Sediments on the NetaJet ferticate sensors and on pump impellers. We have to give frequent maintenance of cleaning. Chemical reaction between fertilizer, separate application of minerals and proteins. Sulfate accumulation in substrate periodic wash. Actually, usually one day of the week, usually on a weekend, Saturday or Sunday, is a day where people wash the substrate, applying only water with acid and no fertilizer, and also washing the hydraulic system, opening the washing valves of the main line, of the secondary pipe, and of the drip lines. Calculating fertilizers availability for plant. It is difficult to control, but we inject by quantity or proportional with no EC target. we use fertilizer method for each tank. We inject in a precise way, but later on, when the fertilizer is in the substrate, we have difficulty to know when the nutrient will be released. We can measure the nutrient level in the substrate and in the drainage water. It will help us to know what is the available concentration of each nutrient for the plant. Okay, so we saw the first challenge, which is the EC control. Let's go through the second challenge, which is pH control. pH control is done by applying acids that neutralize the bicarbonates that we have in the irrigation water. Organic acids such as citric acid are more expensive and weaker than non-organic acids such as sulfuric, phosphoric, nitric, and that are not allowed. So we have, let's talk about three options. The citric acid can be used, but it is expensive. Okay, so it is usually not used because of its cost. Sulfuric acid, as we know, is the cheapest acid, the strongest one, but unfortunately it is not allowed. We are left with the option of sulfurous acid. Sulfurous acid produced by the sulfur burner. We can see this is a comparison between cost comparison between different source of acid made by a company called Sweetwater, which produces a sulfur burner. This is their sulfur burner. There are many sulfur burners that are built in small companies, but it has some, everything has its details, and it's better to have a proven product and use it. But some build their own sulfur burners. The concept of the sulfur burner is that we start with a micronized solid sulfur, 98.5%. It's very pure. It has been put in a tank and goes to the burner along with oxygen. We need oxygen for burning and heat. We have the sulfur. We have the sulfur dioxide gas, which is the production of the burning. When we combine the gas with water, we get sulfurous acid. It's not sulfuric acid. Sulfuric acid will have SO4 and not SO3. And we get in the discharge of this burner an acid solution with pH 2, around 2. Okay, so since irrigations are short, 2 to 5 minutes, and acid is weak, it is better to pre-treat the water with acid in the reservoir. You can see a reservoir as a tank and also an open reservoir. The burner is installed on the opposite side of the irrigation pump suction to allow dilution of the acid in the reservoir water before suction. Yes. If we put the suction on the side of the burner, the irrigation pump suction will suck pH 2. We don't want it to suck pH 2. We want it to use or to suck pH around 5.5, 6, okay, which will go to the irrigation room. It is not easy to achieve pH uniformity in big reservoirs, although the high volume avoids fast changes. The control is usually being done manually. The operator measures manually the pH of the reservoir water, and he goes every 1 hour to check. If he couldn't check the water after 1 hour, no big deal, because it's a weak acid and the water volume is big, so the changes are slow. It is an advantage. Some farmers, the last point, some farmers send a small part of the acid solution to another tank and keep recycling the water in this tank in order to get a more concentrated solution, and from there pass it to the acid tank of the NetaJet for a fine adjustment of the pH during irrigation. The injection from this tank is proportional, liters per cubic meter, with a pH target. If in the EC we didn't ask for EC, in the pH we can ask for a pH target, and we do it. We can also control algae using the sulfur burner. It is basically done lowering the pH to a level of 3. In the evening, when it can be done, the reservoir is left with small amount of water, and the sulfur burner is operated to lower the pH to 3. It is left like this overnight to kill the algae. In the early morning, water is added to dilute the acid till the desired pH is achieved. It's a clever method that doesn't involve additional application of product. The same sulfurous acid that is used for acidify to lower the pH, same amount is used, but on a smaller volume, lowering the pH to 3, killing the algae, and then with additional water, we bring it to the same level. This is a clever method that I learned from a farmer. What are the limitations of sulfur burner in substrates? For organic matter oxidation, for system maintenance, chlorine is one of the options, but since the reservoir of Blueberries farm is treated with sulfurous acid to a pH lower than 6, chlorine cannot be applied. Okay, the combination of chlorine in a pH lower than 6 forms a gas. When this gas comes in contact with the diaphragm, it can create bubbles, as you can see in the image on the right side in front of the dripper's inlet. Sorry, we have a bubble. Obviously, this diaphragm will not regulate anymore. This is an auto-compensated dripper, and the diaphragm needs to move and regulate the flow. This diaphragm will not do the job anymore. And this dripper is also non-leakage, so it won't do the job, and this dripper will continue leaking at the end of the irrigation. So it has to be replaced. There's no solution for that. The third challenge is the application of beneficial products. And we talk about microorganisms that are applied as fungicides. Usually, they are beneficial fungi like trichodermas. The problem is that if they are applied all the time in one of the fertilizer tanks, they can sit on one of the proteins or organic particles and start growing into the dripper. They also can clog clog the filter. So what we recommend is to apply it as a special application and then wash it out of the system where it has to act. Now we want the microorganisms in the substrate where they protect the roots against pathogens, and they help mineralize the organic complex. They have several benefits. So they can be used, obviously, but as a special application, washing the product immediately after its application. The transport time calculation is very, very important when we want to wash a product out of the system and leave the system cleaner. So I suggest warmly to add it to the hydraulic design, and we do it. We provide to our clients a table with transport time. Transport time is the time needed to a product to reach from the injection point to the last dripper. Okay, and it can be calculated. It also can be measured. We can start injecting an acid and measure pH change, or fertilizer and measure EC change, or a color. It can be any product that gives color to the water. Iron chelate, for example, in conventional fertilization is used for that. But the changes are not so sharp when it is measured, but it gives some idea. So it's important to know it. This value will not change along the years if you don't make any change in the hydraulic design. So once you know the value, it will serve you for many applications and for many years. So it's important to do it once, and you have the data. In many cases, there are living microorganisms in the substrate. They can be worms that are introduced to the substrate to mineralize organic matter, or mycorrhizas that live in symbiosis with the root. They enjoy the sugars that comes to the roots from the foliage, and they help the nutrient uptake from soilless to the roots. So it's a win-win situation. They are applied also in blueberries, and when we give some maintenance, chemical maintenance to the system, we have to consider that we will damage, we will harm some of the living microorganisms that we have in the roots and in the substrate. So we have to apply the minimum amount needed, and also to wash afterwards. So let's continue with the summary. For pH control, we use sulfur burner and pre-acidification treatment. Beneficial product application, wash immediately after the application. And now I think we have an open space for some questions if you have. Do we have some questions, or should we continue? Okay, so I think I'll continue, and we'll see some questions at the end.
Yes,
what are nטפים solutions for soilless, for organic soilless, drip products and maintenance? In soilless, we must use CNL drippers. What are CNL drippers? CNL is compensated non-leakage. Okay, CNL. all drippers that are used in substrate must be auto-compensated and also non-leakage. This is the only option. We had clients that asked us not to put non-leakage drippers, and we ended changing the drippers to non-leakage drippers. Non-leakage drippers prevent water drainage at the lower parts at the end of each irrigation. The same diaphragm that is regulating when pressure goes down in the system. We close the valve, okay? We irrigated, then irrigation is finished, we close the valve, pressure starts to go down in the drip lines. When pressure gets to the closing pressure and below, the dripper gets closed. It stops leaking, and we have the drip lines full of water ready to the next pulse. So first of all, we don't have extra water leakage or drainage at the lower parts at the end of each irrigation. If we have drainage at the lower parts, we can have too much water at that parts, and plants may get sick. It leaves the lines full of solution, so when the valve opens, all drippers start dripping at the same time. This is very important when we use short pulses, 2 to 5 minutes. Yes, because if we don't use a CNL and we have the drip lines at the beginning of every pulse empty, there is a filling time. This filling time, some drippers start dripping, giving water and fertilizer to some plants, and some plants still don't get it. So we have an uniform irrigation in the filling time. So we want to avoid zero filling time, and we have it when we use CNL drippers. Okay, so we said we must use CNL drippers, but a static organic solution may cause problems. What are the problems? Small protein particles may gather to bigger ones, get heavier, and sediment on drip lines walls. Low solubility minerals such as calcium and potassium may sediment as well. Now, while waiting to the next irrigation during the day, solution's temperature increases, accelerating biological activity and reproduction. So we may get more biological activity and clogging if we apply our microorganisms and don't wash immediately. While waiting to the next irrigation at night, solution's temperature decreases. Now we have the opposite problem, and mineral solubility decreases as well. So we may have solubility problems. 1 minute, please. Okay, we have several options with PC or auto-compensated drippers. We have 3 options in Nטפים. We have the Uniram or Uniwhite, we have the PCJ, and we have the PC. Okay, we use in organic only Uniram and Uniwhite. We don't use the bottom 2, which is the PCJ and PC, and the reason is that PC and PCJ has a much smaller filter than Uniram. The two bottom, PC and PCJ, are used commonly. They're very good drippers, but for conventional fertilizing, it is not for organic. Okay, the difference is very, very big, from 2 square millimeters in PC and PCJ. We have in Uniram 130, 150 square millimeters. So the difference is huge. This is why we use only Uniram. It has big filter, and also it has very wide water passage and high turbulence. So what are the solutions for organic blueberries in soilless? The best option is the one that we see on the left. We can see 4 drippers for each bag or for each pot. We call it a uni-white skip. Why skip? Because the distance between, or the separation between drippers is not uniform. We skip. So we have drippers every 15 centimeters when we are on the bag, and then we skip. We open a wider separation that depends on the separation or the distance between bags. If we have between bags 50 centimeters, so we use a skip of 15, 35. If we have 60 centimeters, we use 15, 45, etc. This is our best or favorite option. The drippers, better that they will be of 1.6 to 2.3 liters per hour. And before going to the next one, it's very important to discuss advantages and disadvantages with the farmers, that they know what they will face as challenges or disadvantages in the future. In the case of this solution, they have to be aware that the polyethylene has length changes with the temperature. Okay, when temperature goes high, it expands, and drippers may go to the edge of the bag, or if drip lines are not tensed properly, they can also go out of the bag. So we recommend to tense the drip lines when it is hot, and this is how we ensure that the drippers will stay inside the bag, even though when it is hot. Drippers always have to be located upwards to prevent sediments on the filter, on the drippers filter. And when it is located on a bag, as you can see here, the bag gives an advantage because the weight of the drip line makes it possible that the dripper will touch the substrate. Okay, so once the drop falls out of the dripper, it touches the substrate and will not flow along the dripper, as can happen when we locate 2 drip lines on a rigid pot. On the right, we can see a pot. Imagine two drip lines. They will be on the air, because usually the pot is not filled to the top, so the drip line may stay in the air, and if there's a slope, the drop may slide on the drip line and fall near the pot wall. So some people, when they have a deep slope, they just we have some rings that we can put to stop the sliding of the drop, or they can just put a rope around the drip lines very near to the dripper. Okay, let's go to the next solution that we can see in the pot. There are 2 drippers per pot. The flow of this dripper is double the flow of the four drippers that we saw on the left picture. It gives it an advantage, because when we have high flow dripper, the water passage is wider and it is more resistant for clogging. But we have a problem. We have a problem. What to do with the water distribution? Usually, when we go out of a dripper and we want to distribute the water in more than one point, we need to use an arrow dripper, as we can see on the right. This arrow dripper has a filter and has a labyrinth. This labyrinth creates a resistance that makes it possible to distribute the water that comes off the dripper uniformly between the stakes. But when we grow organically, we get problems here. In the labyrinth, we have low velocity, and the solution stays even though when the irrigation was finished, the fertilizer solution stays in the labyrinth and doesn't slide down, so it gets clogged with the time. So we don't use the arrow dripper. We use just a spike that leads the drops downwards. It doesn't have any resistance. This is why the uniformity here is not as good as with arrow drippers, but we try to avoid arrow drippers. So it is a solution preferred by some farmers, but we recommend the solution on the left with 4 drippers, 1.6, 2.3 in the skip solution. We have a very unique solution to connect microtubes and spikes to an integral dripper, as it is the Uniram. We put a zipper. This zipper, you can order it and just put it on the pipeline tightly, and it will lead the drops through the microtubes and to the spikes. Dr. Zip, it is called. Now, the washing of the system is very, very important. We said that we have short irrigation, 2 to 5 minutes. In substrate, the substrate cannot hold so much water, so irrigation pulses have to be short. If we will put a long irrigation, if we'll irrigate with long irrigations, we will have very high drainage because the substrate has a limited capacity of water retention. So we give short pulses, 2 to 5 minutes. So it demands an efficient and fast way of washing. We cannot send a person and ask him to wash many pipelines in 2 minutes if we do it one by one. But if we'll connect several drip lines to a pipe that has only one valve, so the operator will have to open only one valve, and opening this valve, he will wash maybe 30 pipelines. This is much easier, and we know that if things are easy to do, people will do it correctly and at the right frequency and time. So we have to remember that we must use CNL drippers. So, and CNL drippers, as we saw, are more delicate, and we have to wash them more frequently. So we need a good system for washing. The washing valves at the end of the pipe can be automatic and can be manual as well. Okay, so you can see that the blue, well, let's start with the purple one. The purple line is the secondary pipe, and at the opposite side we have the washing pipes. Usually we put, for every valve, we separate into 2 or more washing pipes to get higher velocity and wash with higher pressure and higher velocity. Always the secondary pipe has to be in the higher part of the field, and the washing pipe has to be at the lower. We insist on this because we want the sediments, all the solids, to flow downwards and accumulate in the pipe when irrigation is finished. If we put it the opposite, it will flow back, the solids will flow back to the secondary, and obviously will cause more clogging. For flow monitoring, it's very important to have a constant monitoring of the shift's flow in the controller to detect changes. Every valve, every shift has its flow. It is a calculated flow. The multiplication between the number of drippers by its flow. It is also a measured flow. We have a water meter in the irrigation room that measures the actual flow of every shift. So it's very important to compare between the calculated and the actual flows, and to monitor the change flow during the time. It's easy to do it in the controller because everything is registered in the historic information. Then what I also recommend is to mark several drippers uniformly distributed in the field, in the valve, and always visit the same drippers and collect water to know what its actual flow. Okay, you can put it in an Excel sheet table and make a graph, and once you see a decrease in the flow, you know that you have to react. Okay, you're starting to have clogging problems and you have to wash. So it's very important, the monitoring of the flow of the individual drippers and the flow in the main line. When we have clogging problems, if it is carbonates or some kinds of fertilizer, we can apply a lower pH, apply acid in a lower pH and clean the carbonates. For organic matter, which is the main problem in growing organically in soils, we have to apply chlorine, but we said and we saw that we have a problem there. The best solution is to apply a hydrogen peroxide, and it's better not to wait to a clogging situation. It's better to apply as a prevention and to apply it weekly. Okay, if you apply weekly 100 parts per million during 30 minutes as a minimum, you can get a good control of your organic sediments and keep the system clean. If you have a clogging problem, you can go up to 1,000 ppm or even more. You can take the drip lines down in order not to kill your microorganisms, and apply a higher dose. It will not harm the dripper or the dripper's diaphragm. There's no problem with that, and you can do it. There are some products that we can use. There are products 50%, but not everywhere they are registered with OMRI. There is 35% products with OMRI certification. I made a very fast calculation for weekly application with a flow of 45 cubic meters per hour per hectare. If we apply during 30 minutes or half an hour, with a concentration of 167 milliliters per cubic meter, with a cost of $0.6 per liter, we get a cost of $2.25 per hectare per application. So as you can see, it's not costly, and it's very, very recommended to use. Remember that the drippers that we use in substrates are drippers, they must be auto-compensated and non-leakage, so they're quite they're expensive if we compare it to regular drippers or non-compensated drippers, and they have to last for many years. So we want to take care of them and to give them good maintenance and ensure their good functionality and long life. Okay, we can use for applying the hydrogen peroxide, we can use the extra tank that we saw before in the irrigation room. We can inject in the valve, and we can also use in the irrigation room, we can use electromagnetic pumps. We use here in Mexico Spanish pump, DOSIM. You have to calculate the capacity of the pump. There are different capacities. It's also adjustable, but you have to calculate the capacity of the pump according to the flow and the doses that you want to give. Okay, this was my presentation. Let's open the discussion for questions. Okay, the first question is, why are the lines white? Okay, I'm getting the questions in my WhatsApp. So the first question is, why are the lines white? Is it to keep lower temperature in the liquid circulating through the line? Is this a common practice in open field crops? Okay, it's a good question. The pipelines have two colors. They're basically black. They're basically black and white. Okay, so black is to the inside to prevent light transmission. We know that light transmission develops algae, and it is needed to some microorganisms, and we don't want algae and microorganisms inside our hydraulic system. And also light entering the solution will elevate its temperature, which will reduce the oxygen content of the solution, microorganisms inside the system. The outer layer is black to reflect the light, to prevent the heating of the black layer, and this is how we prevent the solution from getting heated. It is very important in the beginning of the crop. When we plant, we have the drip lines totally exposed to the sun, so it gets heated. We irrigate also with lower frequencies, so between irrigation and irrigation. One minute, please. They say they don't hear me well. Let's see. Okay, now I can see the questions. I will get closer. I hope that you will hear me better. Okay, so let's continue with this. So in the beginning after planting, in the beginning, the drip line is totally exposed to the sun, and the solution inside the drip line may get heated if we use black pipeline. So we use always in substrate or in soilless, we always use black and white drip lines. In open field, it is not used. In blueberries, we have to consider another point, that it is pruned once in a year. So we start again, like with small plants with the drip line exposed. So it's not that we need it only in the beginning, and then later on we can enjoy the shade of the foliage and have the drip line in a more fresh or more cool environment. So we have this situation in the beginning of every year, and pruning is done usually in the hot season. So we must use black and white. Okay, this is the first question. I have overly acidic media and need to increase pH instead. How do I do that organically? If you have enough bicarbonates in your water, if you have pH around 7, it's enough to avoid a situation where your soilless, your media pH will go too low. You have to be careful. If you have an acidic situation, try to avoid the use of perlite, because perlite is made of aluminum. It's aluminum silicate, and it can liberate aluminum in pH lower than 4.54. And aluminum, as we know, is toxic for the plant. Okay, you can add calcium carbonate to the substrate, but not through the drip system. You can apply it or integrate it into the substrate, or apply it below the dripper, and slowly it will release. Okay, but if you have bicarbonates in your water above 1.5 milliequivalents, you will accumulate bicarbonates along the way. You can also play with the relation between ammonium and nitrate fertilizer. Apply less ammonium, even though that we know that blueberries process better ammonium than nitrate. So you need to apply ammonium, but if you see that your pH is going too low, try to reduce your ammonium to the minimum minimum necessary level. Some more questions in my WhatsApp. If the fertilizer has a lot of TSS, is it not better to leave it sedimenting without mixing? Yeah, what you can do is you can many growers do it. When you empty your fertilizer to the tank, you can pass it through like a mesh, and you can capture all or main part of your sediments. You have to filter it. Obviously, you can avoid agitating and leave it to sediment. Take in consideration that your suction point, it's better to have it higher. You can put it around 30 centimeters or even 40 if you don't agitate the tank. But it can be done. What will be the best way for cleaning the tanks? If you do it periodically, you will not have a thick layer of sediments. So you'll just wash it wash it with water. You can, I wanted to say rub it, but putting a person into a fertilizer tank when it's organic, it's not something that people will do. But you can rub it with a brush, with a long stick. Try to brush it if you have a thick layer, and just add water and wash it. It's important, as I said, to have the washing outlet at the lowest point in order to be able to clean it well. If you have your washing point elevated, you will always have some sediments left, so it's not recommended. I see some more questions from Giri A. Hydroponic system, there is a microorganism development, and here more using chemical fertilizer, residual content is present on vegetables. I didn't get the question exactly. You have microorganisms in your system. Mineral fertilizers don't harm them. You have to be careful with fungicides or bactericides if you apply them. When you maintain the system, you have to be careful. But otherwise, mineral fertilizer will not, or chemical fertilizer will not harm them. I hope that I understood the question correctly. Another question, I assume from India, for Vishal Kumar. Can we use proteolytic microbes in the substrate so that non-chelated minerals are also made available in protein-based fertilizers? Yes, whatever you can use. You can use a bacteria that mineralize proteins with no problem. Cheng from China, I think. Is it difficult to continue the lecture here? Can I have a copy of the PowerPoint? I leave it for the organizers. I think it is available, but I'm not sure. Another question from Wilmalan B. Whether seaweed can use as media. There are many types of substrate. First, it has to have the organic certification. It may be used, but if it doesn't have the certification, you will have problems when you want to sell your product. So you have to see the certification issue, and then you have to analyze the chemical and the physical characters of the substrate, the water retention, the porosity, aeration percentage, salinity. If it has high salinity, you have to wash. Sometimes the washing is being done only by water. Sometimes if it has a lot of sodium, if it is a seaweed, probably it will have high level of sodium. You will have to apply probably calcium to make the cation exchange between the calcium and the sodium, and then to wash. But if you check all chemical and physical characters, and you find it suitable, and you get the certification, it can be used. Everything that you do, I recommend to do a small trial comparing with the commercial substrate that is commonly used, to see if it performs better or not.